Hello, my name is Balaji Kalli. As a part of this assignment, Advanced Artificial Intelligence, I selected a topic to present here, which is third person imitation learning. And I want to share my PPT. Yeah, this is my topic, third person imitation learning. And yeah, coming to the next slide, which is abstract. Reinforcement learning makes it possible to train agents capable of achieving sophisticated goals in complex and uncertain environments. A key difficulty in reinforcement learning is specifying a reward function for an agent to optimize. Traditionally, imitation learning in RL has been used to overcome this problem. Unfortunately, hitherto, imitation learning methods tends to require that demonstrations are supplied to the first person. The agent is provided with a sequence of states and specifications of actions that it should be actions to be taken. While powerful, this kind of imitation learning is limited by the relative hard problem of collection first person demonstrations. Humans address this problem by learning from the third person demonstrations. They observe other human perform tasks, interfere in the tasks, and accomplish the same tasks themselves. And coming to the next slide, here we describe a method for unsupervised third person imitation learning. Here, the term third person refers to the training of an agent, like correctly to achieve a simple goal in simple environment when it is provided a demonstration of a teacher achieving the same goal but from the different viewpoint. And unsupervised refers to the fact that the agent receives only these third person demonstrations and it is not provided like a correspondent difference between the teacher and the student tastes. Here, the key findings of our approach, the decent development is domain confusion can be used to produce domain independent in features that are essential for trainings. We present successful third person demonstrations, learning experiments in the point mass, reacher, and inverted pendulum domains to support our methodology. And coming to the next slide, which is Introduction to Third Party Imitation Learning. Reinforcement learning, RL, is used to educate agents to maximize reward in vast, like unknownable, sophisticated environments. Recent studies by MNH, Scullman, and Levin ETAL have demonstrated the success using the deep learning and reinforcement learning approaches to play video games and robotics. This promising field of research has a lot of potential for future applications, and it made even more sophisticating, fascinating by the speed at which RL algorithm capabilities have been developing. The necessity of explicitly specifying a reward function is one of the main drawbacks of RL. The reward function our agent receives must be maximizer that is perfectly recover to appropriate behavior for each task which we want to complete. The weakness is addressed by the field of reinvestment learning IRL. And coming to the next slide, here surprisingly we find that the simple approach have been solved the problems which is presented over here. You know, from the left to right, there are three dominants we consider as point mass, reacher, and pendulum. And coming to the top row, which is the third person view, is demonstrated as like the teacher demonstration. And coming to the bottom row, which is the agent's view in their version of environment. Here, we see the camera angles are differed by 40 degrees angles. And and coming to the third slides, like the third person view, the poles are different here with color actually. The violet represents the third person view, which is on the top, and the bluish green, which is the agent's view, which is on the downside, the third one. And coming to the sixth slide, next slide, here the motivation and significance. It is important to create an algorithm for third person imitation learning, future development in the class of algorithms, which enables people to quickly teach robots new skills, abilities, which will be considerably advanced at the state of robotics. Our method must be unsupervised, which is crucial. By observing individuals around us, we're able to learn new things fast and effectively. And coming to the next slide, background. Yeah. A discrete time function horizon discounted Markov decision process, which is MDP, is represented by tuple. Here you can see the tuple M equal to SAPR. Here S is state set, A is action set, and here the P is transition probability distribution. And coming to the R, which is reward function, and here P naught is initial state distribution. And coming to the gamma, which is discount factor, and finally T is horizon. In this, the first person imitation learning setting, we are not given the reward function. Instead, we given the traces by an expert who acts according to unknown policy pi e. Formally, the third person imitation learning probably, like the problem can be stated as suppose like we given two Markov decision processes, which is m pi e and m pi theta. And here coming to the next slide, which is the third person imitation learning algorithm, we can take the game formulation here. Even when the policies are implemented in diverse contexts, this method is distinguished between the expert and beginner policies with success, as observations rather than direct state access are more frequent available in the third person learning. We will now deal with the observations, which is OT, rather than ST, which is states, representing the expert traces. And coming to the next slide, which is the architecture diagram of third person imitation learning. And here we can see the image here, coming images at time, which is t and t plus 4 are sent through the future extractor. Here you can see the octane of FOT, f of ot, and f of ot plus 4. Firstly, in order to determine whether the samples were taken from expert or non-expert trajectories, they are first concatenated. And coming to this, and the next, a domain label is predicted using f of ot. And back to the propagation destroys information that may have been used to discriminate between two domains by flipping the sign of domain loss LD. And lastly, which is TRPO, uses the classes probabilities that are calculated using the domain neutral feature vector as a cost signal. And coming to the next slide, these are like reward versus iteration, and you can see the meaning: reach a reward versus iteration, inverted pendulum reward versus iteration. And the next one is point reward versus iteration. Here we see in the first, the training is quite unstable due to the confusion, you can see the confusion domain in the domain. However, after several iterations, the possible, the policies eventually head towards the reasonable local minima, which is standard deviation over the reward. And coming to the next slide, next one, finally, we note that the extracted future represented using the complete tasks or in the domain antagonist, and the next one, these are the reacher domain class accuracy versus iteration. And the middle one is pendulum domain class accuracy versus iteration. And the next one is point domain class accuracy versus the iteration. And you can see in the next slide, which is point experiment third person versus baselines. Here, like learning curves for the third person iteration versus baselines. And here you can see mm, the Velo and domain confusion reacher, Velo and domain confusion inverted pendulum, and the last one is Velo and domain confusion point. And you can see here the reacher reward versus domain confusion's coefficient, and the pendulum reward versus domain confusion coefficient. And as it is the red one and it is on the confusion, yeah. And coming to the last one, point reward versus domain confusion coefficient. And here, this is reacher reward versus uh, look ahead frames, and inverted pendulum reward versus look ahead frames. And coming to the last one, point reward versus look ahead frames. And you can see here the point camera angle versus reward. Here you can see the reacher camera angle versus reward. Here the difference is in between the degrees, and coming to the next slide, which is point experiment third person versus baselines. Here you can see the learning curves for the third person imitation versus three baselines. Here the first one is RL with true reward, and the second one is first person imitation, and the third one is attempting to use first person features on the third person agent. And coming to the next slide, here it is the reacher experiment third person versus baseline. And you can see the learning curves for third person imitation versus three baselines. The first baseline is RL with true reward, and the second one is first person imitation, and the coming third one is attempting to use first person features on the third person agent. And you can see the next slide, which is the strengths and the weaknesses. And coming to the strengths of the third person imitation learning, it makes it possible to train agents capable of achieving sophisticated goals in complex and uncertain environments. And coming to the weakness, it is the requirement of demonstration data or some way, or to obtain a supervised signal to desired behavior. And in many applications, obtaining such as supervised data is inexpensive or not even possible. And coming to the next one, here the final one, we discussed the issue of third person limitation forward in this presentation. We contend that this issue will become the more significant in the future, as generative um, adversarial learning and reinforcement learning techniques advance and the price of gathering first person data stays high. Um we provided an algorithm here and to handle the straightforwardness of the third person imitation challenges, and is based on like a generative adversarial imitation learning. uh, and that's up to this one here. Hope you understand the concept of hope you understand the concept here of third person imitation learning. And that's it for me for today. This is Balaji Kali signing off. Jai Hind.